Hello class. Today we're going to go through the bare necessities of exoplanets. And I'm going to call it Exoplanets 101. So, let's get to it. Does anyone here know what an exoplanet is? So start off with a really basic. Shout out. No, you guys know. The general. Yes?
Planet that's outside the solar system.
Perfect. That is exactly right. So, yeah, give her a round of applause. So it's a planet from outside our solar system. Now, the next question is, can anyone name it? No, that's okay.
Technical 1B is empty.
Sorry?
Technical 1B.
Yes, that is an exoplanet.
B.
Yeah. So, round of applause for Paul. So the closest exoplanet to us. This hasn't been updated. Well, the closest exoplanet to us, because I remembered it, I'm a smart person, is Proxima Centauri b. So, Proxima Centauri, the closest star. Well, guess what? It has exoplanets around it. And it's 4.25 light years away. Not blah light years. I don't know who wrote that. Not me. And yes, there's over 5,000 exoplanets been discovered so far, and that number is climbing. There is a whole database full of these different parameters of all these different exoplanets. And some here you see artist interpretations of some exoplanets. So there is a shit ton of them. So let's go over the types of exoplanets you might find first of all. So the first type is a terrestrial planet. So this is a small rocky planet that may or may not have an atmosphere. Now, can anyone here tell me some terrestrial planets in the solar system?
Mars.
Mars, yes. Mars is a terrestrial planet. Any more? No, you're not allowed. You're an astronomer. No astronomers allowed.
Pluto.
No, not Pluto. Earth, yes, you are standing on a terrestrial planet. Earth is a terrestrial planet. And the other two are Mercury and Venus. So our foremost innermost planets are terrestrials. And they're actually quite rare in observations, right? They're quite small planets, so they're smaller, well, they're about the size of the Earth or smaller. And we find it very difficult to actually detect these things because of their size. So it could be that there is genuinely 4% of all exoplanets are terrestrials, or more likely is that we need more expensive, more powerful telescopes to image them. So yes, we need shiny new telescopes. So the second type that we're going to go through tonight are called super-Earths. So these are planets which are larger than Earth, but smaller than Neptune. And to be honest with you, I really hate the name super-Earth because they're not Earth-like at all. They can be, but more often than not, they're not. So what I mean by this is we have two examples here. So the first one we have Kepler 138d. It is covered in a planet-wide ocean, which is about 2,000 kilometers deep. To put that into perspective, that's 150 times deeper than the Mariana Trench. So it is a colossal ocean. Also, the planet down the bottom there is 55 Cancri E. It is a lava world. So think of your Mustafar of Star Wars, it's that sort of burning hellscape. So yeah, they're not Earth-like paradises at all. And yeah, we have no super-Earths in our solar system. Earth is the largest terrestrial planet. We have no rocky planets which are larger than that, and the rest of them are gas giants. And they make up about 30% of what we see, or what we detect in exoplanets. So about 30% of those 5,000 are super-Earths. Now the next one is Neptune-like exoplanets. So can anyone tell me what solar system planets are Neptune-like?
Neptune.
There you go. Sorry, that was a bit of a stupid question. Neptune, but you also have Uranus as well. Yeah, they're gassy planets similar to Neptune. And of course, they are comprised of mostly gas, such as Neptune and Uranus. And yeah, Uranus and Neptune, two in the solar system, and they make up about 35% of all exoplanet observations, making them the most common exoplanet type that we find in the universe. So, and there's some lovely, weird and wonderful ones that I'm going to talk to you about later as well. So the next type is gas giants. So as the name suggests, they are giant and they're full of gas. And they are hundreds of times the mass of the Earth. To put it into perspective, Jupiter is about 300 times the mass of the Earth. So if you think of gas giant, think Jupiter. And there are two in our solar system. I've already named one. The second one is Saturn. So we've covered all the solar system planets in our exoplanet types as well. And yes, they make up about 19% of all exoplanets that have ever been detected. So yeah, we can detect them very well because they are big. And then the very last one that I'm going to talk to you about tonight is hot Jupiters. So as the name suggests, they are Jupiter-like, but they are really up close and personal with their stars, and they are absolutely boiling because of it. And there's a lovely animation in the bottom there about the planet called Kep 9b. No, not Kep 9b, Kelt 9b, sorry. And what you see here is the exoplanet is so close to its host star that its atmosphere is getting eroded by the harsh radiation thrown out by the star, and it forms like a little tail behind it as it orbits around its star, which is terrifying, to be honest. So yeah, and yeah, we don't have any big gas giants between us and the Sun. There are no hot Jupiters in the solar system, and they make up about 11% of all detections so far. So again, still quite common in the universe, if you like. So I'm going to talk to you now about two methods in which we detect exoplanets. Right, only two. So this makes up about 75% of the detections of exoplanets, and it's called the transit method. So what this means is you have an exoplanet which passes in front of its star. So this GIF or animation you see here is that of Mercury transiting the Sun. So exactly the same thing happens with exoplanets. And when that happens, when this little exoplanet passes in front of its star, it blocks out some of the starlight. It causes a very slight dip in the grand scheme of things, but astronomers are able to measure that dip and actually say, okay, this dip occurs once every few days or a few months. Periodically, this must be caused by something in orbit, and it must be an exoplanet. And the bigger the dip, bigger the exoplanet is, right? And yeah, you can measure the size and the orbital period from this method as well. Now the second one is called radial velocity, and for this I need help from you guys. So I'm just gonna, there you go. So this gets a bit interactive. I want you all to turn to the person next to you and smile at them. Give them a wave. If you know them really well, give them a wave. Yeah? Good. Now I want you to turn to the table next to you and give them a wave. Come on, we're all friendly here. You won't bite much. Right. Now you are all acting as one object, one mass. You're all like a hive mind, right? You are a star. You are my star. Consider me as an exoplanet. My whole world revolves around you, right? I am caught in your gravitational field, and you are exerting that gravitational force on me so I don't run away, right? However, from Newton's third law, every force has an equal and opposite force, right? So my weight on the stage is pressing down on the stage, but the stage is also pressing up on me, so I'm not falling through the floor, for example. So that must mean that me, as an exoplanet, must exert a force on my star as well, right? So what I want you all to do in your seats, just give a little wiggle. Give a little wiggle. That's it. Give a little wiggle. Excellent. that is the exoplanets force on the stars. So astronomers can actually measure the stars wiggle. I kid you not, they call them like stellar wiggles, where the exoplanet, as it orbits, wiggles the star back and forth, and that's what we call the radial velocity method. And it actually accounts for something like 20% of all exoplanet detections, so it's still not as popular as transits. But when you can't measure a transit, because it isn't passing in front of our line of sight, which is in front of the star, then we use the radial velocity method. Thank you all for participating. Can you all give yourselves a round of applause? So yeah, to finish things off, I'm just going to go over my favourite weird and wonderful exoplanets. So yeah, let's get started with that. First one, Michelle was blocking it, but that is WASP, WASP 12b. Now, astronomers aren't really great at naming planets, so I'm just going to give them all nicknames. This one's called the Dark Egg Planet, and I will explain why that's the case in a minute. So it is a hot Jupiter. It is way too close to its host star. It takes about a day to orbit this star from WASP 12b, so it is really, really close. Because it's so close to its host star, the intense gravitational force exerted on the exoplanet molds it into an egg shape. So it's not spherical, it is egg-shaped. Now we come to the dark part of the dark egg planet, and it absorbs 94% of the light from that star. And so it gives it like this sort of colour of asphalt appearance. And you all know if you wear black in the summer, you get really, really warm. So it has this knock-on effect that it's over 2,600 degrees C average temperature, so it can get way hotter than that as well. And yes, because it is so close to its star, it will get ripped to shreds in the next sort of few million years. So it's not looking good for this planet. But it's cool because it's egg-shaped. We don't usually see egg-shaped stuff in space, so they're all spherical, just boring. This one is cool because this is egg-shaped. GJ504b, or as I like to call it, the Barbie planet. Why? It's pink. It's a pink planet. This planet was directly imaged. It's a big gas giant, meaning because of its size, we can directly image it. And here you go. Here's the image, and this little spot here is the Barbie planet. It is really bright. It is a baby. It's still forming, and it's about 200 degrees. And because we were able to directly image it as well, we found out its colour. Now we only have like maybe 2 planets where we actually know the colours of them. This is one of them. The other one is blue, but blue is boring. We live on a blue planet, but a pink planet, that's cool, in my opinion. So yeah, the next one, I'm glad the lights are blocking out half of its name because it's a horrible name. It is BSR B1257 plus 12C, or as I like to call it, or as well the International Astronomy Union calls it, poltergeist. I'll tell you why in a minute. It is a super Earth, which you see in the bottom corner over there, and it orbits the inner skeleton of an undead star known as a pulsar. So this is a star that has long since exploded as a supernova, and what's left behind is its core, and it's energetically spinning at over 10,000 times per minute. Now that's insane. And as it does this, you see these 2 bright jets out from the star. I should probably point out that is the star. You see these 2 bright jets coming out of it. Those are pulsar jets, so it likely showers these planets in a lot of radiation. Gamma ray, X-ray, all that jazz. And it was the first exoplanet to be discovered, all the way back in 1992. And it used a technique similar to our radial velocity detection method, so all the wiggles. But instead of being a wiggle of a normal star, it's a wiggle of a pulsar. So same method, just different object. And you're probably wondering why it's called poltergeist. It's a bit of a spooky name, isn't it? Well, there was an International Astronomy Union committee meeting to try and name some of these planets, because to be honest with you, the scientific astronomical name of it is a bit, it's terrible, right? Nobody's going to remember that. So they set about starting to name some planets, and these were one of the first few because, yeah, the name was terrible. So the star itself is called Lich, and if any of you play D&D or Dungeons and Dragons, then you know Lich is a powerful undead wizard, which is kind of cool. Drogon is a zombie in Norse mythology, so that's where that name comes from. Poltergeists, we all know, are ghosts that make things go bump in the night and stuff. So there's a bit of a spooky theme going on here because they're all doomed worlds orbiting an undead star. So yeah. Now the next one is, you might have heard this in the news recently. Who has shared K218b in the news? Yes, the astronomers, a few people are back, excellent. So you know what this next part is going to be about. K218b is the tentative sea shanty planet environmental comet. It is a super-Earth or a Neptune-like. The boundary between these two planet types is actually very blurred. It doesn't depend on mass, it depends on their composition, and it's very difficult to actually determine the composition for each individual exoplanet. But the jury is leaning more towards it being a super-Earth at the moment, so that's good. And it's a potential water world, so again, from its chemical composition, we think that it is likely covered in vast oceans. However, in April, a potential biomarker was discovered here. So it was dimethyl sulfide, and what I mean by a biomarker is that it could be an indicator to life, which is kind of cool. The press found it really cool, started freaking out that there's aliens on this planet, but we haven't gotten there yet. So a little tip for you if you find news articles like that. We don't actually know if there's life on the planet unless we actually go to the planet and visit it and like take samples in like water or wave to an alien or something. Unless we see it, we don't know for sure. So, but yeah, it's kind of cool anyway. So who knows? There may be life on this planet. And that brings us to the end. But I'd like to have a few notable mentions of some other extreme planets before we leave. HD 189733b, please think of a name for it, because it's terrible. It rains molten glass here at over 5,000 miles per hour, which is kind of cool. I would like to visit this planet, I don't know about you guys. Kepler 51d, it is known as a super-puff planet. So what that means is it is roughly the size of Saturn, and that should say 3 times greater Earth's mass. 6 times more massive than the Earth. So it's huge as Saturn, but it's got a few Earth masses contained within it. And just to put it into perspective, Saturn is about 100 or so Earth masses. So this thing is really, really not dense at all. In fact, it's about 10 times less dense than cotton candy. So yeah, it's called a superpuff, and I love it. And then the next one, you've got 55 Cancri E. As I mentioned earlier, it is a lava planet, it is over 1,000 degrees C, and thanks to the naming committee that I mentioned earlier, its name is actually Janssen, which is a Dutch spectacle maker. So yeah. And if you want to know more, then I recommend, I won't put links up on here, but if you Google NASA Exoplanet Catalogue, there's lovely models of these exoplanet systems. You can see if they're in the habitable zone or not. You can know things like their mass and orbital period. Then you've also got the Exoplanet Travel Bureau, which is like a interactive traveler's guide, if you like, to some exoplanets. They have lovely travelers posters, which you see here, which you might be able to win tonight in our quiz. And you can actually visit the surface of some of these planets and have a little look around, and they'll tell you cool and fun facts about all the planets, or some of the planets there. So please check them out if you want to find out more. And thank you. That's it. Do you have any questions? Oh, yes, Paul.
So you had
exoplanets that these activities reveal information?
I think at the moment it's roughly about 1% of all the exoplanets have been imaged. It's just you need them big, you need them bright in order to image them with the current technology that we have. There was one at the back at the moment. Oh
I think
yeah.
it's around 50 to 58 planets up in the AP mass. So, yeah, it's not many of them.
Back.
It's maybe a stupid question.
No, no question is a super question.
How do you tell the difference between, like, when you're measuring the dip
Yeah.
of star brightness?
Yeah.
How do you tell the difference between, like, if something's happening between us now,
Yeah.
if it's closer to me, there'll be a bigger dip in the brightness, versus if it's closer to you, it'll be a smaller dip. How do
Yeah,
you
that's
tell
true.
whether it's the distance or the size of the planet?
Yeah, so from measuring just the star, we can find out the distance. So, and it also depends on its period, so it's orbital period. So we don't just measure one transit and say, oh, okay, there's an exoplanet there. We need to measure multiple in order to actually ensure that this thing is orbiting. So there's been a lot of false alarms in the media over the last few years of people just measuring one transit and saying, oh, it's a planet. Like there was one a few years ago about a super Saturn, which had these colossal rings. But that's been disproven now because we haven't been able to get that second transit. So it must have been like some sort of rogue gas cloud drifting off the space. So it is very difficult in order to actually know whether it's like something big that's just passing in the foreground, but we just really need to rely on that periodicity or that regular dips in order to actually know that it's an exoplanet or not. Does that answer your question?
I was wondering, just to add to that, usually if a planet is in the star system, for instance, there's another limit on the planet sizes, which is 13 Jupiter. So the size of 13 Jupiters, which would only be still, like 1% of the star size. So if it's blocking out more than 1 or 2%, it's definitely not part of that system anyway. But like Holly just said, with the period, and this is where the bias of hot Jupiters against Earth's come from, because a hot Jupiter with a short period is a lot easier to see multiple orbits, right, than any other. So.
Anything else? Yes.
Do you know why the water planet's pink?
Why it's pink?
Yeah.
They say it's sort of like a magenta colour. It wasn't necessarily pink, but more magenta. But magenta is still pink. Fight me. Please don't. I'm scared. But it's recently formed, so the heat it's generated from being formed sort of leaks through the clouds that it has, and it gives off this pink appearance. Okay, I'll leave it there. Oh, go on.
I wanted to ask, I can remember it saying all the glass in the planet.
Very good question. So we know it has. I'll start. We have detected silicates in its atmosphere. So glass is made of silicate. Yeah, glass is made of silicates. And because of the temperature that it's at, we know it'll be sort of these silicates or sand will melt together to form glass. And I'm not sure how they measured the winds, but we know that it's very windy on this planet, 5,000 miles per hour. So it'll be raining molten glass sideways on this planet, just from inferring these two things. It might not be glass, it might be some completely new, weird crystal or something, I don't know. But we like to infer things, so yeah. Right at the back again.
How many exoplanets has James University been responsible for finding?
Ooh, responsible finding.
Is it like a significant percentage of the ones that we know exist?
Yeah, I don't actually know. I will admit something. I'm not actually an exoplanet person. I just find them cool. I'm not sure, but what the JWST has been doing is analysing their atmospheres a lot more. So For example, I think it was K218b was analysed for JWST, so it's very useful for JWST to analyse atmospheres, because it's so powerful and shiny and we love it. But in 2029, hopefully we'll have Ariel, which will be able to uncover more, find the compositions of more exoplanets, because they're specifically built for doing that. So stay tuned. I think we'll wrap up there because we're running out of time. So yeah, thank you. Thank you everyone.
Thank you, Holly.